The Mechanical Engineering Lab at the KU Leuven was one of the first worldwide to perform full 3D force-controlled peg-in-hole insertions with very narrow clearance. Since then, theoretical and practical work has focused on the implementation of force control on either velocity or position-controlled industrial robots, on real systems as well as in simulation. A palletizing operation demonstrates the ability of the force-controlled robot to deal with uncertainties in workpiece location and geometry. The force controller establishes a stable contact and proves to be very robust against the unmodelled slope in the pallet. The blue arrows in the centre of the moving object represent the measured contact forces and torques. A 3D seam-following example demonstrates the tracking facility of the force-controlled robot system. Measured forces and velocities are used to keep a constant orientation with respect to the followed contour in two orthogonal Cartesian directions. Opening of a door is an example in which the motion freedom of the robot is constrained by a kinematic chain. The robot is asked to pull the door open. The force controller generates the circular motion based on the measured force errors. The position of the door's hinge does not have to be known. Another application of force control in the presence of kinematic chains is the hinging of a rack. This simulation is performed for the European Space Agency's Columbus Space Lab. Manual deburring is a non-ergonomic and tedious task. A force-controlled robot removes the burrs by applying a constant force normal to the contour and a tangential force adapted to the burr size. The robot is able to track the contour even without knowing the object's geometry. This application eliminates the need for accurate clamping devices. The tracking facility of the force controller allows to automatically teach contouring paths, for example the glue path for the contour of a car door. A small set of simple force control commands is sufficient to specify the task. The robot follows the surface of a workpiece while maintaining a desired contact force. Meanwhile, it learns the curvature of the contour. The same information is extracted from a geometric model of the workpiece or from a camera image. The use of this curvature information significantly increases the performance of the task. This means smaller force errors and higher execution speed. Two robots perform a synchronized tracking task. The follower robot receives online information about the motion of the leader robot and uses this data as feed forward for its force controller. The force controller detects when the peg crosses the rim of the hole. It pushes the peg into a stable three-point contact. Each contact is modelled by a 5 degrees of freedom kinematic chain. The time-varying and non-linear motion specification to align the peg and the hole is derived from this kinematic model. A reinforcement learning controller is capable of increasing the insertion speed without increasing the contact forces. The system's initial performance is shown on the left. The performance after 100 learning steps is shown on the right. The force control software combines inputs from multiple sensors. Here, both a force sensor and a 6 degrees of freedom trackball control the robot's motion. The robot has a plan of the nominal world. By searching for expected contact transitions, the uncertainties between the nominal and the real world are resolved. The insertion strategy for irregularly shaped cylindrical objects uses both force control and the representation of the hole's contour to determine the exact location of the hole.